Hello everybody, welcome to topic 4. In this topic we are going to cover some formula that you can use in calculating the present value of benefit and costs, which is one core component in cost-benefit analysis. You need to understand, you need to get yourself familiar with the formula sheet like this one, and in the exam, in the midterm, in the final exams, you will be given such a formula sheet as well. So you don't need to memorize it, but you need to understand it. Okay. When you are calculating the present value of benefit and the costs which occur in the future, it's always good to use a timeline to denote the cash flow pattern. This is year 0, 1, 2, 3, 4, so on and so forth. One thing I want to make you be aware of is that this 1 here is end of year 1, end of year 1, also beginning of year 2. Okay, so 1 here is end of year 1 and beginning of year 2. Why is this the case? Well, let's starting from this point, time 0, which is currently. So if you move one step forward, then you get into the beginning of year 1. And you keep moving, you arrive at here, then it is the end of year 1. Then you move another step forward, then you get it into beginning of year 2, and so on and so forth, so on and forth. So make sure you get it right here. Alright. Suppose at present times I have $1 in hand. Then I can invest this $1, say deposit in the bank or invest in the stock market, buying bonds, etc. And the interest rate or discount rate is I. Then in in 1 year's time, what is the dollar you can have in your account in a year's time? Clearly, it should be 1 multiplied by 1 plus I. In another year's time, in year 2, you can get 1 multiplied 1 plus I multiplied by 1 plus I. Or it is just 1 plus I to the power 2. In year 3, another year, so it's 1 plus I to the power 2 previous year's dollar multiplied by 1 plus I. So which is 1 plus I to the power 3. So on and so forth. Clearly, you are going to see that you observe a pattern now. In year n, you should get 1 plus I to the power 1 minus 1 multiplied by 1 plus I to the power n. So if you invest $1 today, and in years time you get this many dollars back. And then investment, we call this compounding. But we are not for our purpose, we are not interested in getting the future value. Instead, we are going to think backward. We are going to say that in the future there's this many dollar. What's the present value of this many dollar? Clearly, it should be $1, right? It should be $1. Okay. If we have, say, present value, say currently I have X dollar. In the future, I have Y dollar. Say in years time, there's Y dollar cash inflow. And what's the associate present value? What's the present value of this Y dollar in year n? Suppose it's X dollar. If it's X dollar, you invest it, then in year n you should get X multiplied by 1 plus I to the power n is equal to Y. That's the Y dollar you have in year n. So clearly, present value, the X dollar should be equal to Y multiplied by 1 plus I to the power negative n. Just multiply both sides by 1 plus I to the power negative n 1 plus I to the power negative n. And this cancels out with this one. So x is equal to this. Or let me write it, x is present value is equal to future value in year n multiplied by 1 plus I to the power minus n. Okay. And this is a very important formula, discounting formula that we are going to frequently use it in the calculating the present value of benefit and cost. So make sure you understand. Make sure you understand this. Present value is equal to future value in year n multiplied by 1 plus I to the power minus n. Okay, that's the formula for discounting future value back into present time. Frequently, cash flow or benefit or costs, they occur as a kind of regular payments over the regular time intervals, and we call this annuity. For example, say a project may involve a benefit of $1 million or $2 million every year for the next 10 years. And what is the present value of this cash inflow or this annuity? We call this annuity. Alright, to derive this annuity, let me first to derive the present value of this annuity. Let me first look at a mathematical tool we call geometric series. And by the way, the derivation here is not examples, so I won't ask you to derive a formula in the exams. So all you need to do is to understand them and be able to apply them. Okay, let's say you have this series AR. First term is A, second term is AR, and AR squared, AR to the power 3 until AR to the power n. So this is the series you have. You have n terms here. Then what's the sum of these n terms? If we want to sum it up, what's the formula for the sum? To get a formula, let's first look at each terms in the series. We will be able to observe a pattern here. So from A to AR, just A multiplied by R, right? So AR divided by A will be equal to R. Third term divided by second term, AR squared divided by AR, you get R. This term divided by this term, AR cubed divided by AR squared is equal to R. So clearly, if we do all this for all the n terms, then we are going to find that the next term divided by previous term, we always get these common ratios. And we call this geometric series. Geometric series. So that's the R is the common ratio, A is the initial terms. Okay. So our aim is to find the formula of sum of these n terms. Now one trick is that let me multiply both sides by the common ratios. So I'm going to multiply left-hand side by a common ratio, then right-hand side by the same common ratio. So A multiplied by I get AR. AR multiplied by R, I get AR squared. So on and so forth. Then there's a term here, AR to the power n minus 1. AR to the power n minus 1, I get A multiplied by R, I get ARN. Then the last terms, ARN multiplied by R, I get ARN plus 1. Okay, so now what I want to do is I want to subtract them from subtract this one from this one. So Sn minus R Sn. Sn here is common term, you can pull it out. So it's equal to 1 minus R Sn. And this should be equal to these terms. Subtract this term from these terms on the right hand side. So this one, clearly we can find that we can cancel out a lot of terms in between. This one cancel out this one, 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 and this one, this one. Okay, excuse me. So A remain here. Now the last term here is negative because we subtract this one from here. Minus 1. Pull the A out. A 1 minus R A minus 1. Then divide by both sides by 1 minus R. And we get Sn is equal to A 1 minus R M plus 1 divided by 1 minus R. So that's the formula for the sum of this geometric series. Okay, I'm going to write it here. We're going to use this to derive the present value of annuities. So Sn is equal to A 1 minus R M plus 1 divided by 1 minus R. That's the sum of first n terms. What's going to happen if say I let n approach infinity? I have infinitely many n's. So I sum over this infinity many n terms. What's going to happen? Two things can happen. First one, it could converge. Second one, it could diverge, explode. We are only interested in the situation when it converge. We can get a finite sum. Okay. So if R less than 1, between 0 and 1, this common ratio. And for our purpose, R will be equivalent to, let's say, discount rate. And discount rate usually is between 0 and 1. Okay. Then what's going to happen if n approaches infinity? Or I'm going to write this one, limit n approach infinity, Sn. What's going to happen to Sn, these terms? Clearly, you should see that. Let me just write out this is limit n approach infinity, A 1 minus R n plus 1 minus R. Look at this formula here. Look at this equation here. Where does the n appear? So n only appears here in these terms. So what's going to happen when we let n approach infinity? Well, it depends on what's going to happen when R to the power n plus 1. Whether is it going to converge or diverge depends on these terms. So since R is between 0 and 1, so if multiply by R, if I multiply R by another R, which is R squared, so R is between 0 and 1, so it becomes smaller. If I multiply R squared by another R, it becomes smaller. So clearly, as n approaches infinity, R to the power n plus 1 approaches 0. So this term approaches 0, so this term disappears. So it's equal to A 1 minus R. Okay, so that's given that R is between 0 and 1, and we sum over infinity, many n terms, we end up in having a finite numbers. Okay, let me just write it here. So S in approaching infinity is A divided by 1 over R. Alright, so that's the formula. The sum of n terms of a geometric series. And this is the sum of infinite terms of the geometric series, given that R is between 0 and 1. That's all what we are interested in. Alright, okay, now we are ready to derive the present value of an annuity. Okay, let me use the timeline again. 0, 1, 2, 3, 4, 5, and so forth. So this annuity occurs every period. There's R dollar cash inflow, cash inflow, cash inflow, cash inflow for n years. So what is the present value of this annuity? That's our purpose. Okay. To get the present value, first one, push the year $1 back to present. So using the discount formula we derived previously. So it's discount rate is I. Okay. So R divided by I. R divided by 1 plus I. Okay. That's the discount rate, 1 plus I. Second year's R, push it back, you get R 1 plus I squared. Okay. Third year, R 1 plus I to the power 3. Fourth year, R 1 plus I to the power 4. So on and so forth until nth year. Now it's R 1 plus I to the power of n. Okay, then we want to sum them up. We want to sum this term, this term, this term, this term, this term up. So there are terms. Okay. Now let's observe the pattern. Let's observe each terms. What kind of pattern can we observe? So first term is this term. If we divided the second terms, R 1 plus I squared divided by the first term, so that's R 1 plus I. So we get 1 over 1 plus I. If we divide third term by the second terms, again we get 1 over 1 plus I, so on and so forth. So actually it's a geometric series. Geometric series. With the first term is equal A is equal to this. Common ratio is equal to 1 over 1 plus I. So clearly we can apply the formula here. So the present value of this annuity, first term is R over 1 plus I. 1 minus the common ratio. Common ratio is 1 plus I to the power n plus 1. Divided by 1 minus common ratio. Common ratio is 1 over 1 plus I. Okay. Now let's simplify this formula. So multiply both top and bottom by 1 plus I. So this 1 plus I cancel out with this one. So this one multiply inside. So on the top we get R minus 1 plus I over multiply this one inside. So it's 1 plus I minus 1. So it's just I. Okay, or we can write it this way. R multiplied by 1 minus 1 plus I power of n plus 1 divided by I. And we call this annuity factor actually. Annuity. Okay, that's the present value of an annuity. I'm going to write it here on top. Multiply 1 minus divided by I. Okay, that's the present value of this annuity. Okay. What about this R dollar cash flows occur forever, not just n years, but infinity many years? Then what's the present value of this? Equivalently, let's say that's equivalent to say let's let n approach infinity. What's going to happen? Clearly, if you look at this formula here, if n approach infinity, then this term 1 over 1 plus I is less than 1. bigger than 0. So this one becomes smaller, smaller, smaller until it becomes 0. So then if this R, this cash inflow, this R dollar cash flow occurred forever, or we call it perpetuity. Then the present value of this perpetuity is these terms. In the Pearl infinity, this term disappear. So it's quite simple actually. R over I. R over I. R over I. So that's perpetuity. Sometimes annuity could be deferred annuity. Say this annuity does not start from year 1, just from year 2, and for n years. Then how to calculate this present value? You can do it in 2 steps. First one, you can discount all this one back to year 1. You apply this formula, push everything back to year 1. Then follow back to year 0. And sometimes annuity could be annuity due, or annuity is occurred at the beginning of year. Say this annuity R dollar occurs at the beginning of year 1, so that's year 0 for n year. Then what is the present value of this annuity? So clearly for the first R dollar is already present value. You don't need to push it back. So now you just push the remaining n minus 1 terms back into present value using this formula. Alright. So that's annuity and the perpetuity. So the next formula, the next topic I want to talk about is we call it internal rate of return. Internal rate of return. For any project, we want to calculate the present value of cost and present value of benefit. So present value of benefit, is equal to sum of each year's benefit, sum of present value of each year's benefit. So each year benefit, let me denote B, which is T. Discounted back, that's benefit occurred in year T. So discounted back, I is the discount rate, minus T, negative, okay. Then sum from year 1 to n. This project lasts for n years. And certainly we want to calculate the present value of cost as well. And cost, again, let me use C to denote the cost. And the cost could occur in each year. So year T. If cost occur in year T, discounted back that's the present value of the cost happened in year T, then sum over 0 to n. So currently, usually you got to pay a cost at present time. Okay. So what is the internal rate of return? Internal rate of return is the discount rate I such that present value of benefit is equal to present value of costs. That's the definition of internal rate of return. So clearly, if you look at the present value of benefits, certainly you are going to find that it's not surprising that this one, the present value of benefit, should depend on I. Present value of cost should also depend on I as well. So certainly, or in principle, there exists at least one I such that present value of benefit is equal to present value of cost. Or this equation is equal to this equation. present value of cost. And this, I'm gonna change I to R such that I denote it as such that I know it's we call this internal rate of return. Okay, internal rate of return. Look at this equation. Clearly, it's not an easy job to solve what the R is. To solve what R, because here it is in terms of high order polynomials. So I don't think anybody is able to solve this by hand manually. But fortunately, we have Excel to do this job for you. I'm going to show you on the computer. Excel has a function which is called IRR, internal rate of return. Let me just give you a simple examples. Assume that if you want to invest in a project, assume that initially you got the cost at year 0 is $20,000 for beginning a business, and the income will be $12,000, $15,000, 18, 21, 26 in the next 5 years that follows. Then one thing that you want to know is, if you invest in this business, what kind of rate of return you can get, or what's the internal rate of return, or what is the rate of return such that your present value of benefit, present value of income here is equal to present value of costs. Okay, so you can put all this value and this present value, this cost and income into the Excel like this. And now note that the first term is negative because it's a cost. It involves a cash outflow. And then what you do is insert a function IRR, and let Excel know that from the range of cells to obtain data. So here is J28 from this cell to J33, and then go. So 8.66%. So if you invest in this project and this business, you can get a rate of return of 8.66%. So now to decide whether it's good to invest in this business or not, then you got to compare this rate of return, internal rate of return, with your cost of capital. Say if you borrow it from bank charge you 5%. Then clearly it's profitable. It's good to invest in this business because you can earn 8.6% here. So that's our internal rate of return. However, there's a shortcoming. There's a disadvantage of our internal rate of returns because we have the IRR is actually essentially a solution to this equation. This equation is high order polynomials, and we can end up and have more than one solutions to these equations. Say it could be one solution is 8%, the other solution is 3.5%. In these cases, we don't know which rate is the correct one. Okay, that's a big disadvantage of IRR, internal rate of return. All right. The next formula I want to talk about is discount rate. So far we have taken this discount rate as being given, but then we assume that discount rate or the compounding occurs as the frequency of compounding is the same as the frequency of cash inflow and outflow, but which is not necessarily true. Not necessarily true. I'm going to use